Hi everyone, so today we will be learning about gas stoichiometry at STP and non STP conditions. So when you say STP, it means that it has a standard temperature and pressure. So the values are already given at standard conditions. So there are values predetermined for the temperature and the pressure. So at STP in gas stoichiometry, when we say for problems at STP conditions, we have to take note that 1 mole of any gas, it has to be 1 mole of any gas, has a volume of 22.4 liters. So it means that in every mole of a given gas, the volume of it is fixed and it is 22.4 liters. The second note we want to look at is that volume to volume ratios in a balanced equation can also be considered as mole to mole ratios at STP. So the balanced equation, the equation should be balanced, and the ratio for volume to volume can be considered as mole to mole. So instead, when we have 1 liter of a liter of this has a liter of that, we have a mole of this has a mole of that. So to better describe these rules or notes, let's look at example number 1, where we have an excess of hydrogen reacts with 14.01 grams of nitrogen. How many liters of ammonia are produced at STP? So hydrogen is of course a gas. It's H2, hydrogen gas. And N2 is a nitrogen gas. So from this, we can say that an excess of hydrogen gas reacts with nitrogen gas. How many liters of ammonia are produced at STP? So ammonia is a covalent or molecular compound given as NH3. And then we need to balance this equation. So this is the first step. We want to see a balanced equation. So we need to multiply 3 on the hydrogen gas in the reactant side, and then we have to multiply 2 in the product side for ammonia or NH3. Now we have 6 hydrogen atoms in the reactant side and also 6 on the product side, and 2 hydrogen atoms for both reactant and product sides. Now, the next step is to use dimensional analysis. So remember at STP for gas stoichiometry, 1 mole of any gas has a volume of 22.4 liters. So we first write the given values. We have 14.01 grams of N2. So when we say dimensional analysis, we opt to cancel out units to achieve what we're looking for. So our units, end units for the final answer should be liters of NH3 or liters of ammonia. So in dimensional analysis, we combine values, of course following rules of stoichiometry. And to do this, we have 14.01 grams of nitrogen gas, and we know that 1 mole of nitrogen gas is 28.02 grams of it. So how did we come up with this value? So if you can recall, we should solve for the molar mass of N2. So N2, the molar mass for this is 2 times its atomic mass from your periodic table if you can check your periodic table, nitrogen has a 14.01 atomic mass. So you just write it up here. We have 14.01, then we have 28.02. Okay, so just going to erase this one. We solve for the molar mass of nitrogen gas. Then we look for the mole to mole ratio. So we have these moles in the product and reactant side. We have 2 moles of NH3 has 1 mole of N2. Note that we want to cancel this one and to arrive liters of NH3 or ammonia. So this one is also cancelled. And then we use the first rule, where 1 mole of any gas has a volume of 22.4 liters. So we have a fixed value of 22.4 liters. So we have in 1 mole of NH3 have 22.4 liters of NH3. Then we cancel the units. So the final answer would be 22.4 liters of ammonia. So this is the final answer. Now let's proceed to non-STP conditions. So previously we have one example for gas stoichiometry problems in STP condition. Now we have for non-STP. So we have also again 2 notes here. We have for non-STP conditions, you will need to use ideal gas law for this. If you can recall, we have ideal gas law equation given by PV equals nRT. So this was the ideal gas law. You can check this one in your module as well. It's a prerequisite topic before proceeding to gas stoichiometry. So the first note is, if you're given the liters in the start with ideal gas law, then do a stoichiometric conversion using dimensional analysis. So this is pretty simple. There are problems where the volume is given first, and all you have to do is then start do the stoichiometric conversion using dimensional analysis. However, if you're looking for the liters when the volume is not given, start with a stoichiometric conversion and then use the ideal gas law. So the ideal gas law here is used at the last step. So to better illustrate this, let's look at example number 2. So example number 2 says that to calculate the mass of potassium chlorate needed to produce 5 liters of oxygen at 25 degrees Celsius and 1 atmospheric pressure. So a continuation for this problem will be potassium chlorate decomposes into oxygen and potassium chloride. So now we want to emphasize that this gas stoichiometry problem involves decomposition. So if you can recall the difference between decomposition and combustion, in decomposition, since it from the word decompose, we're expecting O2 or oxygen in the product side. So the first step would be to draw the skeleton of the equation. We have the potassium chlorate potassium chlorate is given as, this compound is KClO3. And it decomposes into oxygen and potassium chloride. So let's start with potassium chloride given by KCl plus oxygen. So oxygen is definitely O2. It's the same as hydrogen gas, which is H2, and nitrogen gas, which is N2. So the next step is to balance this out. We have 1 KCl and 1 Cl. So we multiply the reactant side to 2, and then the KCl in the product side also 2, and then 3 for the oxygen gas. So we have 6 oxygen gas, 2 potassium, and 2 Cl. Now we're ready to proceed to step 2. So before anything else, it's better to write down the given. And so the pressure for this is 1 atmospheric pressure. And the volume is given as 5 liters of O2. And then the temperature is given as 25 degrees Celsius. And if we're dealing with temperature in ideal gas law, if you recall the PV equals nRT, this temperature should always be in Kelvin. So for this to be in Kelvin, we just add 273. Therefore, we have 298 Kelvin for the temperature. And then we're looking for, since it's the value of R is from our module, let's recall, R is the ideal gas constant. So I'll just copy and paste it here. So we have this one. This screenshot is from your week 2 module. So R is the ideal gas constant. So the 3 most common formulations of R are given by this one. So we use the first one. We use this one if the given pressure is in atm. So now we know what R to use. We have 0.0821 L atm over mole of Kelvin. And so we're missing the N here. So we're actually looking for the moles in the first part. So the step 3 would be to solve for the moles of O2 using the equation, the ideal gas equation, the PV and RT. Now, let's use this one. The step 3 would be PV equals nRT, and we plug in what we have. So we actually have N equals PV over RT. Then we have pressure is 1 atm. The volume is 5 liters. The R is 0.0821 L atm over mole Kelvin. And the temperature is 298 Kelvin. And just we cancel the common units. We have to cancel this one and this one and this one also. We have L here. So the final answer would be, no, this one is not the final answer, but it's for the moles. So we have 0.0204 mole of O2. Now we have the complete values for the ideal gas law. So what we're actually looking for is the mass of potassium chlorate. So our last unit should end up with G of KClO3. So this is just the first step. Now we have the N here. Let's proceed to step 4, where we use stoichiometry to convert from moles of O2 to grams of KClO3. So we use the value we got from step 3. We have 0.0204. No, this is not correct. This is actually 0.204. So we have 0.204 mole of O2. Then by dimensional analysis, we know that for every 2 mole of KClO3, we have 2 moles of O2. 3 moles of O2. So we use that one. So we have, for 2 mole of KClO3, we have 3 moles of O2. Now we're getting closer. We have to cancel this one and think of the next ratio that we multiply. So first, let us solve for the molar mass of KClO3. So molar mass for this is K is equal to, the atomic mass unit for this is 39.10. If you look at your periodic table again here, so K potassium is 39.10, and Cl is 35.45, and our O is 15.99, or let's just say it's 16. So we just simply solve for the molar mass of the compound. Cl is 35.45, and then we have oxygen, which is, it's O3, it's 3 atoms, and then we have 16. So in total, the sum for this is 122.55 gram per mole. So we interchange this one. We have the reciprocal is the same for, since we're dealing with ratio. It's 122.55 gram of KClO3. There is 1 mole of it, KClO3, and we cancel this one and this one. So the final answer, if we multiply all these values, our final answer would be 33.4 grams of KClO3. And that's it. That's what we're looking for. This is the final answer. It's the grams of potassium chlorate. Here we have the third example, where we are asked for the volume. So it says that calcium carbonate decomposes into calcium oxide and calcium dioxide. So what volume of CO2 forms 5.25 grams of CaCO3 calcium carbonate at 1.02 atm and 25 degrees Celsius? So we are asked for the volume. The volume is not given. So our approach here would be as per the second note. If you're looking for the liters, and we are looking for the liters, start with the stoichiometric conversion, and then lastly use the ideal gas law, or the PV and RT. So let's start. As always, let's begin by constructing the equation. We know that calcium carbonate is CaCO3, and it decomposes to, when we say decompose, it can either contain oxygen gas O2 or carbon dioxide in the product side. So we have calcium oxide, and this is actually carbon dioxide. Okay? It's carbon dioxide. This is not, sorry, it's 12:32 a.m. This is carbon dioxide. Carbon. So this is the first step, and we make sure that this equation is balanced. And let's see. Yes, they are balanced. We have 1 mole of Ca on both sides, product and reactant, 1 calcium and 3 oxygen. So we won't be needing to balance that out since it's already balanced. And step 2 is, as per the second note, is to, let's use stoichiometry and convert grams of CaCO3 to moles of CO2, carbon dioxide. So we have the given 5.25 grams of CaCO3, calcium carbonate. Then we know that when we get, in order to get the mole from the gram, we solve for the molar mass first. So we know that 1 mole of CaCO3 can have, let's solve for this manually. We know that Ca is 40.08. Check your atomic mass periodic table. C is 12.01, and O, since you have 3 here, 3 atoms, you have 16. So the total would for this would be 100.09 grams. So I hope you get that one. And I'm just going to erase this one. So we have 100.09 grams CaCO3. So you can cancel this one. Note that our goal here is to convert grams of CaCO3 to moles of CO2. So let's look at the CO2. Let's use the mole to mole ratio. We have 1 mole of CO2 has only 1 mole of CaCO3. And then we cancel this one again. So our final answer would be 1.26 mole of CO2. But actually that's not our final answer. That's this is just our goal for step 2. Our final the most final answer that we want is the volume. What volume of CO2 do we need? Okay, so now since this is mole, this is our N, right? So let's write what we have so far. We have N equals 1.26 mole of CO2. We know that our pressure is 1.02 atm from the given. Our volume is what we're looking for. Our R is, since it's ATM, let's use the first R constant. We have 0.0821 LATM over mole dot K. And then the temperature at 25 degrees Celsius, but we always want it to be in Kelvin, so we add 273, and we have 298 Kelvin for the temperature. Then we solve for V. We have PV and RT, and so we have nRT over P. Now we have 1.26 mole of CO2, 0.0821 of LATM mole dot K, and temperature of 298 Kelvin. 298 Kelvin over the pressure at 1.02 atm. Let's cancel what we can cancel, the mole, the K, the atm. Now we're left with the liters. Now we have solve this one. We have 30.22 liters of CO2. This one is the final answer. We achieved our goal, which is to find the volume of CO2. Okay, and that's it. Thank you for watching.